Yeah. Uh, okay. So good afternoon, everyone. So this was the qualities of measurement from Unit 1. So far we have seen various contents and divided this into various three parts of this unit. One part is about the meaning of instrument, the elements of instrument, and then the static and dynamic characteristics of an instruments. Then from part 1, we have seen what is measurement first. Okay, what is the definition of a measurement? What are the examples of measurement and types of measurement? Direct and indirect measurement we have seen. Then what is instrument in general? So what is the role of instrument in determining or measuring something? Then what are the functions of an instrument, various functions and elements of an instrument we have seen with an example, suitable examples. Then we have studied about the characteristics of an elements like static and dynamic characteristics, everything we studied. And in the part 2, we have studied expansion thermometers, that is liquid expansion thermometer, then solid expansion thermometer like biometallic thermometer, vapor or gas expansion thermometer, like pressure spring thermometers we have studied in the part 2. Then in between, we have studied the various temperature scales, 5 different temperature scales, which are popularly used in every industry. We have seen that one. Then mercury in glass thermometer with their advantages and uses, everything, the principle behind the operation, working principle, everything we have studied in detail, the mercury in glass thermometer. Then we went for the biometallic thermometer. So their principle, uses, working, okay, construction, everything we have studied in detail. Then the last expansion thermometer is vapor or gas expansion thermometer, that is called pressure spring thermometer. We have also studied this one. So all these thermometers so far we have studied. Okay, what is the thermal well, how to fix inside that one. Then pneumatic balance pressure thermometer, the expansion of that pressure spring thermometer. So in order to lower the disadvantages, whatever they are there in the pressure spring thermometer, so this type of construction, pneumatic balance pressure thermometer is possible. Their advantages and disadvantages we have studied in detail earlier. Then today we are going to see this common sources of errors in filled system thermometers. So what are the common sources of errors? Like first one, if you see, the ambient temperature effect is there. Why we are listing out the ambient temperature here? So for example, if you consider, okay, so effects of we say the, or we can say errors in thermometer. So what are the various effects and errors in thermometer which are caused? For example, if you think of the mercury in glass thermometer, so mercury, so inside the glass, okay, this is the overall scale like this. Then here somewhere the bulb will be there. So in this bulb, there will be some filled, mercury will be filled. Will be filled. Okay, this thermometer, since this is the immersion type of thermometer, so what we have to do, we have to take this thermometer and insert into some medium, okay, whose temperature has to be measured, like a water bath, okay, metal bath or something like that. We have to insert in that particular medium. And when you take this bimetallic thermometer also, the same principle. So the bimetallic thermometer, some metal will be there, high thermal coefficient, and some metal with the low thermal coefficient of expansion will be there. Two different coefficient of expansion thermal effects will be there in the bimetallic thermometer. This also we have to immerse into some medium. And if you consider this one, the pressure spring thermometer, in the pressure spring thermometer also, the same thing, we have two capillary and armor will be there. And after a capillary and armor like this, there will be some pressure receiver. Okay, receiver will be there. Okay, here some gauge. Okay, in between some pressure receiver and a pointer will be there. Okay, like this, some scale will be there. So this bulb has to be immersed into some medium. And this also we have to immerse into some medium. So all these are the immersion type of thermometers. Okay, so here the expansion will be different whenever you are dipping only this much part of the thermometer into this liquid means, so the heat conduction will be very less. Okay, there will be some dip effects. Okay, that type of errors will be caused, dip error. Operator sometimes they will be somewhat like lazy or something like that. They will not immerse, okay, completely immerse the thermometer. they will immerse to some extent only. Okay, like dip effects will be caused, like ambient temperature will be somewhat different. Okay, some barometric pressure. Barometric pressure means nothing but atmospheric pressure, like a surrounding pressure, ambient temperature. Okay, therefore they need some compensation in order to have them in a good condition, like a head effect. Like for example, head effect means nothing but this one. So if the thermometer bulb is located at this location, okay, it will not be located at this point. It will be located at upper point, upper elevation or the lower elevation. Whenever this thermometer bulb is deviating from its standard location, there causes a head effect. Okay, like this, we have to study a different effects. So first effect among them is, first is the ambient temperature effect, we will say.
Sir,
Ambient, yes, yes.
Jeevan just now messaged me that he had network issue till now, sir.
Okay,
So he's asking to unlock, sir. I mean, he's requesting.
okay, I have unlocked.
Thank
Yes,
you, sir.
yes, okay. My screen is visible? No, not I think. Okay, so first one is the ambient temperature effect, this one. So what is this ambient temperature effect? So at this thermometer bulb condition, there will be some other ambient conditions. Okay, something, some contaminants will be there, some temperature differences will be there. Okay, at this particular location. So the ambient temperature effect is caused due to the temperature difference between the surrounding atmosphere as well as the measuring bulb. Okay, measuring bulb will have certain temperature TB. Okay, surrounding ambient temperature will have some ambient temperature TA. So because of this difference in TB and TA, so there will be some effects, some errors will be produced. So that type of errors are called ambient temperature affected. Therefore, it needs to be compensated. That ambient temperature compensation needs to be adopted in such type of thermometers. Okay, in expansion, especially this is the special case in the gas expansion thermometer. This pressure spring thermometers, so this will have a special effect. Why? Because whenever there is a difference in the ambient temperatures and the bulb temperatures, what happens? Whatever the pressure which is going inside the capillary and armor, and it is received by this receiver like a pressure gauge, pressure spring. So, okay, this pressure spring deflection will be limited. Okay, it will be limited or it will be more. Okay, anything can be happen due to this temperature difference between ambient and this particular bulb temperature. Okay, then the degree of this ambient error. So whatever the ambient error which is producing here, depending on the temperature range of the instruments, are also in the relative volume of the bulb, capillary and receiving element. And also its ambient temperature effect not only shows on this receiver, but also it also be showed depending on the temperature range. What type of range this particular thermometer will possess, and as well as what is the volume of that particular bulb, what is the volume of this particular, how the capillary is there, how the receiving element is there. Okay, receiving element is pressure spring. Okay, then capillary, this is a capillary and armor. So this is the bulb. Okay, so all things will be affected due to the temperature effects which are caused in the ambient temperature, at the ambient temperature conditions. Okay, I hope this is okay. Ambient temperature effect. Do you understand that one?
Yes, sir.
Okay, then next one is head effect. Okay, then what is the head effect? For example, same thing. Due to the change in the elevation of the bulb, whatever the effects which are caused is called the head effects. So in the head effects, what happens in a pressure thermometer, especially in the pressure type of thermometer, if the elevation, okay, this is the, for example, if you consider this as the standard elevation of the bulb, so that a receiver can receive a accurate temperature prediction or accurate pressure deflection. Okay, so but operator, what he will do, he will locate this bulb at some other elevation or at so lower elevation or the higher elevation. Due to this elevation difference, whatever the effect caused, whatever the pressure difference caused inside this capillary and armor, that will be directly effective in the pressure receiver, pressure spring. Okay, due to this pressure spring, receiver receives a less pressure or the more pressure, there will be an error in the reading. So the head effects in the pressure thermometer is usually caused by placing the thermometer bulb at a considerable higher or lower portion of the elevation than the receiving element. So there should be some ideal position for this one. Otherwise, the operator usually will place the thermometer bulb at higher elevation or the lower elevation. So due to this head effect, the bulb and the receiver, whatever the lesser or greater pressure which is caused, directly it will be showing a effect on this pressure spring, which is nothing but a receiver. And due to this pressure spring and a receiver, there will be an error in the reading of the particular thermometer. So that's what the head effect due to the, that is caused due to the elevation difference. Okay, elevation difference of the, whether it's a higher or whether it's a lower. So due to this difference, whatever the effect is caused, that is called head effect. And third one is the barometric effect. So can anybody say what is barometric pressure? What is the barometric pressure? What is the relationship between atmospheric pressure and barometric pressure? Okay, so barometric pressure is nothing but atmospheric pressure. So barometric pressure or atmospheric pressure or both are same. Okay, so whenever there is a surrounding atmospheric pressure is different compared to the inside bulb temperature, inside bulb pressure, then there is a effect that is called a barometric effect. So barometric effect in the pressure spring thermometers, the error in the instrument reading due to the changes in the barometric pressure. So outside, how much fluctuation is there in the outside pressure, depending on that one, there will be a corresponding or conducive errors will be there. So their error occurs because of the pressure spring deflection. Okay, because of this pressure spring deflection, what happens if the pressure here is very high? Okay, outside the atmospheric pressure is very high like this. So whatever the pressure which is exerting here, that will be caused some effect in the pressure which is induced inside this capillary and armor as well as the bulb. So this induced difference in the pressure, it will directly goes and attack on this receiver, and it will corresponding error values will be resulted in the external and internal, due to this external and internal pressure changes. So corresponding errors will be produced. Usually there should be some compensation for this one. Okay, barometric pressure. For example, what is the barometric pressure? Barometric pressure is nothing but an atmospheric pressure. And also we can say what is absolute pressure. Absolute pressure is nothing but what is atmospheric pressure plus what is the gauge pressure. So gauge pressure means you might have seen in the fluid mechanics course. I hope you already studied the fluid mechanics. Whatever the manometers, whatever the pressures they are measuring now, that is called as a gauge pressure. Okay, U-tube manometer or a inclined tube manometer, we can say. Okay, whatever the pressures they will measuring now, all these pressures are called the gauge pressures. Okay, to calculate the absolute pressure, we have to add this gauge pressure with the atmospheric pressure. Then only it will be called as a absolute pressure. That's the difference between absolute pressure, atmospheric pressure, and gauge pressure. So this atmospheric pressure is also called as a barometric pressure. In the weather stations, this is very popular, barometric pressures. By these conditions only, they will predict whether the rains are coming or not, what type of cyclones are coming. All this will be predicted using this one. Okay, head effect and barometric effect is okay. Do you understand that one?
Yes, sir.
Yes, sir. Okay, then next
Yes, sir.
effect is, I think, immersion effect. Okay, then fourth effect is the immersion effect. Okay, so this immersion effect results from the conduction of heat along with bulb thermal well. By reducing the temperature at the bulb causes an error that is called conduction error, or we can say that as immersion error. If the thermometer bulb is there, okay, for example, mercury in glass thermometer you are considering, you are inserting into a hot water bath. So until this level, your hot water bath is there. Okay, you are inserting this much only. Okay, now how the conduction will happen? By sensing the vapor temperature around this hot water bath. This temperature, the thermometer has to show the temperature here in this condition. And for example, in other condition, for example, this is a hot water bath. In this hot water bath, if you dip your thermometer like this, okay, thermometer bulb like this, So this will give you a correct reading. Why? Because there will be a heat transfer or heat conduction from this hot water bath to the walls of this thermometer or the thermal well of the thermometer. Then a proper conduction will take place. Due to this proper conduction, the mercury which is there inside will be expanded correctly and it will show you accurate reading. So if you are not immersing this one correctly, so it will cause the error values in this one. So due to the limited heat supply between the hot water bath as well as the thermometer, this type of errors are very high in this one. Next we can say this is a dip effect. Okay, this dip effect, usually this dip effect will be caused in the metallic bulb of mercury. Okay, mercury in glass thermometer. For example, the same thermometer is there. If you are immersing into the hot water bath, so before expansion, what is the principle in operation of this mercury in glass thermometer? Just simply whenever there is a heat, okay, which heat energy has to be transformed from the hot water bath to the bulb, and inside the bulb there is a mercury. That mercury has to expand like this. Then only we can read the reading. In the dip effect, what happens? Before expansion of the mercury, the bulb itself will expand. Due to this expansion of the bulb, what happens? The bulb volume will be increased. Okay, because of this volume increased in the bulb, so that will cause a dip effect. That will not show a accurate reading. So third effect is called as a dip effect. So dip effect is nothing but usually in the principle of mercury in glass thermometer, mercury should expand. Mercury should expand, not bulb. Okay, only bulb will hold the mercury inside the bulb. That's the role there. But in the dip effect, what happens? Bulb will expand first. Bulb will expand first. Due to this bulb expansion, what happens? Volume of bulb will be increased. Bulb will be increased. Because of this increased volume of the bulb, whatever the effect is caused, that is called as a dip effect. I hope this is clear. Immersion and dip effect.
Sir.
Yes.
In dip effect, sir, we can't be finding the temperature accurately, sir, because the already bulb is absorbing the temperature and getting their volume expanded.
Yes. That's what effect means. That's an error. Okay, that's an error. Under such conditions, we cannot rely on that particular thermometer. We have to change that one. So in case of metallic bulb of mercury filled system, the metallic bulb expands before expansion of the mercury. Hence the volume of bulb is increased, the pressure reduces. Then the response of the thermometer is slowed down. If the response is slowed down, that type of thermometer, no use of using that type of thermometers. Absolutely right, that one. Okay, Jeevan?
Yes, sir. Yes, sir.
Okay, in summary, there are 5 different types of effects or errors which are induced during the operation of this type of immersion thermometers, especially the pressure spring solid expansion thermometer like bimetallic and this mercury in glass thermometer. So first one will be the ambient effect. So ambient effect is nothing but ambient temperature effect. More preciously, we can call as ambient temperature effect. Due to the difference in the ambient temperature around the bulb, whatever the difference is there, that will be causing a deflection. Okay, negative deflection or a positive deflection in the pressure spring or a bored-on tube. So due to this one, a pointer reading will be showing an error. And next one is head and elevation effect. If the elevation is according to the standard, then it is okay. If the operator is locating this bulb at the higher location or higher elevation or the lower elevation, then there have a difference in the pressure. Due to this difference in the pressure, that pressure difference will be showing an effect on the pressure receiver. Here the pressure receiver is nothing but bored-on tube or pressure spring. The next one is barometric effect. Okay, in the barometric effect, what happens? This due to the ambient condition, ambient pressure, okay, difference in the ambient pressure, or due to the difference in the barometric pressure, or due to the difference in the atmospheric pressure. Whatever the pressure difference is there, whenever internal pressure and the external pressures are deviating largely, then there will be an error which is induced in the deflection, this receiver. Due to this, a deflection error will be caused. And next one is immersion effect. So due to the not properly inserting this bulb into the medium or medium into which the temperature has to be measured. Due to this incomplete immersion of that bulb, what happens? The conduction will not take proper. The heat transfer will not take proper. Due to this improper heat transfer, whatever the readings which are induced will be very low, will be showing. And next one is a dip effect. So usually according to the principle, the mercury which is there inside the metallic bulb, it has to be expanded first. Okay. But in the dip effect, what happens? Before expansion of the mercury itself, the bulb will be expanded. Due to this expanded bulb, the volume will be high. So volume expansion will take place. The bulb will be expanded. Its volume will be expanded. And due to this increased volume, the pressure will be decreased. Okay. Reduced pressure will decrease. So mainly in the operation of this type of thermometers, the pressure is the main criteria. If the pressure itself is decreasing means, so it will not show you an accurate reading. That's the common sources of error in various filled system thermometers. Okay, I hope everybody understood this one.
Yes, sir.
Yeah. So next topic is characteristics of pressure spring thermometer, or characteristics of immersion type of thermometer, we can say, or expansion thermometers, we can say. So three different types of thermometer I have summarized here. The first one is temperature limits. To which extent we can use the mercury thermometer and gas filled thermometer and vapor filled thermometer. So as shown here, the temperature is minus 35 degree Fahrenheit to 1000 degree Fahrenheit. We can accurately reliable on the mercury thermometer. For the temperatures around minus 200 degree centigrade, 200 degree Fahrenheit and 800 degree Fahrenheit, we have to rely on the gas systems are very much good. And in case of vapor system, the temperature range is minus 50 to 600 degree Fahrenheit. And what about the ambient effect or ambient temperature effect on this type of thermometer? So the ambient temperature effect will be there in the mercury in glass thermometer. Why? Because it is operated due to the by sensing or by conduction of the heat around the bulb. So if the heat around the bulb is somewhat deviating or ambient temperature is very much different, then the bulb will have some inaccuracy in the operation of the thermometer. So there will be a ambient temperature effect on the mercury in glass mercury thermometer and gas thermometer, and there is no ambient temperature effect on the vapor filled thermometer. Why? Because vapor has to expand depending on its pressure difference. Okay, vapor pressures will be coming into the operation picture here. The next one is head effect, or the we can say this elevation effect or head effect. So elevation effect will be there in all the three types of thermometers. Then barometric effect. So there is no barometric effect in the mercury thermometer. Why? Because its operation is completely dependent on the temperature, which is conduction, by the conduction of the temperature around the bulb. So the barometric effect is barometric pressure will not have any effect in the mercury in glass thermometer. But whereas the gas thermometer will have a little effect, and the effect of this barometric pressure will be very high in case of vapor thermometer. The next one is a dip effect. So dip effect, since the mercury in glass thermometer or mercury in metallic bulb thermometer are there, so the expansion of that bulbs will be very high, especially in the mercury thermometers. So there will be S for the dip effect, but there is no dip effect in the gas and vapor things. The next one is a response speed, or a speed of response will be usually for the mercury and gas thermometers, the same type of responses will be there, but the response for the vapor filled thermometer will be very high or greater than. Then sensitivity, how easily it is adopting the changes in the surrounding environment. So the greater adaptation will be there for the mercury, and whereas somewhat same adoption will be there for this gas and vapor thermometers. So this is the summary of various types of thermometers. Is that clear?
Yes, sir.
The next one is a part 3. So part 3 is entirely concerned about the thermoelectric effect. So how the electromotive force will come into picture whenever there is a difference in temperatures of the two terminals. Okay, whenever there are two dissimilar wires, if they are held at two different temperatures, so how the heat conduction will take place, how from where the heat conduction will take place, or heat flow will take place from one region to another region, or due to this heat flow from one region to another region, there will be a flow of current from one region to another region. So how that flow of current is there? What is the relationship between that conduction, heat, temperature? Okay, how to measure that EMF value? What is the relationship between this EMF value generated within the thermocouple or a dissimilar wires? Then what is the linearity between the temperature and the EMF value generated? That we have to study in this particular third unit. So the first topic will be thermoelectric temperature measurement and its uses in the industrial thermocouple. So how the industrial thermocouple will be constructed and operated, that will be the main role of this topic. And next, lead wires. So usually there will be two junctions for the thermocouples. Okay, one will be the measuring junction, other one will be the reference junction. So in order to make use of this location, okay, usually the measuring junction will be far away located. Okay, then the receiving junction or the reference junction, we will say, that will be located far away from the measuring junction. To connect this measuring junction and this reference junction, a suitable wires will be used. That is called as a lead wires. Okay, that is called as a lead wires. So we will be studying what type of lead wires are compatible with which type of thermometers. So we will be studying in detail in the lead wires topic. Then materials of construction. What type of construction material we have to use, or like a copper constant and alumel, chromel. Okay, what type of materials are compatible with which type of lead wires and which type of thermocouples, and their specifications, to which extent we can apply that one, to which extent the specifications will be dependent, we will be seeing in this particular topic. So this is also a very small part. We'll just go through. So first one will be the thermoelectricity. So before that one, what is the importance of our thermoelectric temperature, or what is the importance of industrial processing of higher temperatures? Especially when you see the steel industry, steel manufacturing industry, glass manufacturing industry, ceramic industry, or the cement manufacturing industry, there will be a possibility, there will be a chance of determining the temperature or measuring the temperatures greater than 2000 degree Fahrenheit. Okay, nearly 2000 degree Fahrenheit to 3000 degree Fahrenheit temperature we have to measure. Under such conditions, no operator can go and dip the mercury in glass thermometer there. Okay, no operator can go to that point. Okay, he cannot measure that much high temperature by just giving some mercury in glass thermometer, inserting there the mercury in glass thermometer. Our body temperature is very low. Okay, around 95 degree Fahrenheit or 100 degree Fahrenheit or 105 degree Fahrenheit at far away. That's why we can be able to use our mercury in glass thermometer and put it in our mouth. Okay, our mouth is medium under such condition. But what about in the industrial process? They have to measure more than 2000 degree Fahrenheit or more than 3000 degree Fahrenheit. Under such conditions, no operator will go and insert this thermometer in that medium, in that kiln or in that furnace, something like that. We cannot insert that one. Okay, there will be a damages direct whenever there is a direct contact. So because of this advantage, we have to use the thermocouples or some suitable thermoelectric principles we have to use. So the temperature movement between the 1000 and 3000 degree Fahrenheit is usually governed by this particular radiation heat transfer. So radiation heat transfer will be very much advantageous. So why? Because nowadays whatever the pyrometers we are using, due to the radiation phenomena only, we could able to measure the body temperatures without touching us. If it is a mercury in glass thermometer, we have to insert that glass thermometer into our mouth, and after cleaning or after sterilizing that one only, we have to insert into other person's mouth due to this current pandemic. Otherwise, if you insert that mercury in glass thermometer in corona patient mouth, and afterwards if you insert that same thermometer into another healthy person's mouth, then there will be a collapse. Okay, then there will be a clear blunder. So that's why there is a popular use of this radiation heat transfers, especially in the thermocouples and resistance thermometers. So they are very much useful to measure the temperatures from the far away places. Okay, we can stand somewhere else, we can measure the temperature of something, some object from the far away locations. So the thermocouples can also be used for low temperatures of both the gases and also the liquids. So as low as minus 300 degree Fahrenheit is very much possible. Okay, yeah, especially in the case of thermocouples. So see here, in the case of mercury or gas or vapor, so only minus 200 degree Fahrenheit only possible, minus negative temperatures. But whereas using the thermocouples, we can go far away, nearly minus 300 degree Fahrenheit temperatures also we can accurately measure using the thermocouples. So the compared to this filled thermometer, okay, some mercury filled thermometer or gas filled or vapor filled thermometer, okay, compared to this thermometer or immersion type of thermometers, so thermocouples will provide an accurate and much reliable indication of temperature. So they are very much suitable for, especially for the industrial application. Majority of industrial applications, they will be using the thermocouples. Okay, so that's the advantages and that's the principles behind the operation of thermocouples. So thermoelectricity will be playing a major role in manufacturing or in construction of these thermocouples. So just simply assume that there is some thermocouple circuit, a simple thermocouple circuit. So this thermocouple circuit is composed of two dissimilar wires. Okay, they are not equal wires, they are dissimilar, very much dissimilar in their conduction, in their resistance. So they are very much different. So they are joined at two terminals. So one terminal is called as a measuring junction, another terminal is called as a reference junction. Usually this measuring junction temperature will be very high and reference junction temperature will be very low. Okay, then this reference measuring junction will be placed near the medium. Okay, near the kiln or near the furnace. Okay, some manufacturing process near it one. Then this reference junction will be placed at the far away places. Okay, due to this far away places, the temperature reading we can read near here. We can measure the temperature here due to the flow of current or flow of heat from the measuring junction to the reference junction. Due to the flow of heat or due to the flow of heat due to the conduction or due to the flow of current from the measuring junction to reference junction, an electromotive force, thermal EMF we will call, that will be generated here. Due to this generation of thermal EMF, the flow of current from the measuring junction to reference junction will happen. This thermal EMF will be measured using some suitable measuring element, measuring device. Then that device will give a accurate reading between a proportionality relationship or a linear relationship between this thermal EMF generated as well as the temperature which is there in the medium at the measuring junction. Then we can directly read the much reliable and accurate reading of temperature here in the reference junction by standing at a very far away places. So a thermocouple is composed of two dissimilar wires joined together so as to produce an thermal EMF. So this thermal EMF, how it is generated? Due to the temperature difference between the measuring junction and the reference junction. So usually this measuring junction will be located near the medium whose temperature has to be measured. So due to this one, we already know the principles of heat transfer. So heat will be transforming from higher temperature region to lower temperature region. So higher temperature will be the measuring junction and lower temperature will be the reference junction. So due to this phenomena, according to the Fourier's law of heat transfer, the heat conduction or heat transfer will take place from higher temperature region to the lower temperature region. So this heat transfer will take place from the higher temperature to lower temperature. During this one, there is a current flow from the higher temperature to lower temperature. Due to this current flow, there will be a generation of thermal EMF, the thermal electromotive force. So this thermal electromotive force will be generated in these two dissimilar wires, and that generated thermal EMF will be measured using some suitable device, and that device will give you a linear relationship between the temperature which is there in the medium and the relationship between thermal EMF will be generated. Therefore, at this point, we can, at the reference junction point, we can measure our temperature there. That's the thermoelectric effect or thermocouple composition, how to manufacture or how to construct a circuit of thermocouple. Okay, this circuit, is that clear? This circuit, how it is prepared?
Yes, sir. Yes, sir.
Okay, so here the left hand side junction is called as a measuring junction whose temperature is held at T, and right hand junction is called as a reference junction whose temperature is held at TR, which is called as a reference junction temperature TR. So usually due to the difference, the thermal EMF will be generated. So what is the relationship between the current flow and what is the relationship between the thermal EMF? What is the relationship between heat flow? So to classify that one, there are some effects are there. The first effect is called as a Seebeck effect. Okay, the Seebeck effect, what the Seebeck effect is telling. So according to the Seebeck effect, that current flows in a thermoelectric circuit when a temperature at the junctions are different. So current will be flowing. The Seebeck effect is saying that whenever there are two different temperatures are there, two different junctions are located at two different locations. So due to this one, there will be a current flow. When the temperatures at the junctions are different, then the thermal EMF is generated in the circuits, which will be causing the flow of current from one location to the another location. So by the principle of conservation of energy, the energy under static conditions. So whatever the static conditions are there here must come from the absorption of heat from the external sources. So if you want the current to be flowed from one region to another region, there should be absorption of heat from the one location. So since the high temperature region is here, so some object is there whose temperature has to be measured. The heat from this object has to be transformed to this measuring junction. Then that heat has to be absorbed by this measuring junction. Due to this absorption, the heat, after absorbing here, the heat has to evolve from the measuring junction to the reference junction. So how the heat is transforming from higher temperature to lower temperature will be telling by this Seebeck effect. So due to the absorption at the measuring junction, absorption of heat at the measuring junction from the object, the heat will be absorbed here and the heat will be evolved from the measuring junction to the reference junction. That is said by Seebeck effect. So that is here. The current flow in a thermoelectric circuit when the temperatures and tensions are different. Therefore, a thermal EMF generated in the circuit which causes the current flow. By the law of conservation of energy, this current or energy must come from the absorption of heat from the external source. So external source is possible only here. Why? Because the hot object is there here. So because of this hot object, the heat has to be absorbed by this temperature measuring junction. Then heat has to evolve from the this direction. So that is given by this particular Seebeck effect. Is that clear? Seebeck effect?
Yes, sir. Yes, sir.
Then after absorption of this heat, so how the temperature has to travel from the measuring junction to reference junction will be given by the Peltier effect. Next effect is called as a Peltier effect, which will relate the absorption and evaluation of heat at the junctions of thermocouple to the current in the circuit. So how that absorption of heat at this junction and evaluation of heat from this junction to this junction, so how they are related, how they are related to the current flow in the circuit will be telling by this Peltier effect. So it relates the absorption and evaluation of heat at the junctions of the thermocouple to the current flow in the circuit. So under conditions of use, measuring junction is at high temperature and reference junction is at low temperature. So heat is evolved at reference junction and absorbed at the measuring junction in proportion to the flow of current, but independent of method. Okay, we need not consider this, what type of welding we are performing here, whether this is a welding or this is a soldering, whether this is a butt type of welding, whether this is a twisted type of welding. So no matter what type of joint it is, so it has to, heat has to be absorbed at this location from the external object, and it has to travel from this external location to the reference junction, other location of the object. That's said by the particular Peltier effect. Okay, no matter how we are manufacturing the end terminals, whether maybe welded, solder, or just they are brought into intimate contact, no matter, that is not dependent. The Peltier EMF is not at all dependent on the particular welding or soldering or intimate contact. Only the EMF will be generated due to the travel of that heat from the one measuring junction to the another reference junction. So that EMF is called as a Peltier EMF, which is proportional to the current generated, I. So this is called Peltier effect. Is that clear?
Yes, sir. Yes, sir.
Then next one is called as a Joule heating effect. So okay, how this is somewhat nearly equal to this Peltier effect. Only difference is here whatever the Joule EMF generated, that is proportional to the I square, current square. Here in the Peltier effect, Peltier EMF is directly proportional to the current only, but here the square of the current into resistance, the product of square of the current and resistance, the Joule effect is EMF is equal. So EMF is proportional to the product of square of current and resistance. So this is not related to the operation of thermocouple. So we need not to consider this in the operation of thermocouple. Only this is a Joule heating effect, that is irrelevant, but somewhat the effects will be there here. The next one is a Thomson effect. So this Thomson effect will give a relationship between your EMF which is generated in a single homogeneous wire and also the temperature between the ends of the wire. Okay, what is the temperature between the difference between the two junctions? How these temperatures are related with the Thomson EMF. So therefore, Thomson EMF is directly proportional to the temperature, or we can say the difference in the T minus TR. So this T and TR. Okay, that's the function of this Thomson effect. Is that clear? Thomson effect?
Yes, sir. Yes, sir.
So in the operation of thermocouple, three laws are used. One is the Seebeck effect. Next one is Peltier effect and Thomson effect. We can neglect this Joule heating effect. But in the examination, you have to write this Joule heating effect also. The next topic is the laws of thermoelectric circuit composed of homogeneous conductors. Okay, here in the thermocouples, what happens? This is the measuring junction. This is the reference junction. So in between them, there are many wires will be there. This is a simple circuit, but in the complex circuit or the industrial thermocouple setup, there are many wires. Okay, to connect this measuring junction with the reference junction, there are many wires are there. Where we have to connect that wire, whether connecting that wires to this thermocouple measuring junction and reference junction will have an effect on the EMF, will have an effect on the temperature. So how that effect will be there, what type of effect will be there, how we can add the wires in between the circuit, that will be governed by this laws. So that laws are called as laws of thermoelectric circuit composed of homogeneous conductors. So the first one is a laws of homogeneous circuit. So what this law is saying, the electric current cannot be sustained in a single circuit of a single homogeneous metal. However, varying in section by the application of heat alone. So a single electric current cannot be sustained in a single homogeneous circuit. It has to be vary. It has to be a different section. So whatever the thermal EMF which is developed in the thermocouple, when the measuring junction and the reference junctions are apart, okay, they are different. Okay, that EMF will be independent of temperature gradient and its distribution along the wires. The only temperature related to the thermal EMF are the measuring junction temperature and reference junction, and all other intermediate temperatures are of no consequences. So meaning of this one is, for example, okay, for example, the first law is law of homogeneous circuit. So law of homogeneous circuit, what it is saying is, okay, what this law is saying is, whatever the EMF which is generated, if the thermocouple is composed of like this, two dissimilar metals, for example, so the temperature T and temperature TR is there. Whatever the EMF which is generated in this thermocouple, this EMF is only the function of this temperatures. No matter whether the temperature here is different, here is different, here is different, here is different, here is different. So they will not have any effect. So for example, this is T1, T2, T3, T4, T5. If the temperature is T1 different from the T, if this is different, so no matter whatever the intermediate temperatures are there, so thermal EMF generated is only the function of T and TR only. That is called as law of homogeneous circuit. Okay, the thermal EMF developed in the thermocouple when the measuring junction T is at different temperature from the reference junction TR is independent of temperature gradient and its distribution along the wire. The only temperatures related to thermal EMF are the measuring junction temperature and the reference junction temperature TR, and all other intermediate temperatures are of no consequences. So that is called law of homogeneous circuit. Is that clear?
Yes, sir.
Okay, this is not due to any derivation or not due to any facts, only due to the experimental facts. Okay, this law has been given by the experimental facts, not due to anything else. Okay, not they have not proved through any such equations or any derivations. Only this is observed through the experiment. This fact has been observed through the experiment, that one only. So then next law is called law of intermediate metals. Okay, whatever the wires we are inserting, lead wires or any dissimilar wires, whatever we are inserting, that will be entirely dependent on this law. So the algebraic sum of the thermal EMFs in a circuit composed of number of dissimilar metals is 0 if all the circuit is at any uniform temperature. So what this law is saying is, so for example, if there is a thermocouple, okay, some measuring junction is there like this. Okay, then you are adding some intermediate metals like this. Some lead wire you are adding like this. Okay, this is a measuring junction T. Measuring junction T. So this is metal A and this is metal B, and you are adding some lead wire C. Here some joint you are fixing, and here also some joint you are fixing. This is some metal, for example, some metal B only you consider. So if you are joining further with the reference junction like this. Okay, this is TR. And to measure your EMF, you are connecting some galvanometer here like this. Okay, this is to measure the EMF, EMF. What happens here in the metal A, EMF will be generated, that is called as AEMF. And in metal B, the EMF will be generated, that is called as B subscript EMF. And in the metal C, EMF will be generated, that is called as CEMF. So now what this law is saying, law of intermediate metals, law of intermediate metals, it is saying is, so algebraic sum of the first this EMF, AEMF plus this BEMF plus this CEMF, okay, is equal to, it should be equal to 0. Then only the thermocouple will operate properly. Otherwise, there will be an heat difference will come. Somewhat some hot spots will come. some hysteresis will be formed here. So if you don't want to form some hysteresis or result in damage of these thermocouples, we need to have algebraic sum of no matter any thermocouple EMF, it should be equal to 0. That is what said by this law of intermediate metals. So that is the algebraic sum of thermal EMFs in a circuit composed of any number of dissimilar metals is 0 if all the circuit is at uniform temperature. So only necessary condition is the all circuit needs to be at a uniform temperature. So this law follows directly from the second law of thermodynamics. If a net EMF did exist, means if it is net positive, okay, what happens if it is net positive, not equal to 0, means there will be some positive value greater than 0, then what happens, this will result in the reverse flow of heat. So flow of heat has to from T to TR, measuring junction to TR, the flow of heat. Okay, if this condition is not satisfying, all the algebraic sum of thermal EMF is equal to 0. Under such condition, the reverse flow of heat is possible. Okay, that is against the law of second law of thermodynamics. So heat cannot be traveled from this lower temperature region to higher temperature region until unless we are giving some external work. Okay, if you are not giving external work, but it is still traveling from lower temperature to higher temperature, so that is a contrary to the second law of thermodynamics. If that need not to be contrary to the second law of thermodynamics, we have to this condition has to satisfy. Law of intermediate metals condition is algebraic sum of thermal EMF generated in the circuit is equal to 0. That is the fact of this law of intermediate metals. So this law follows directly from the second law of thermodynamics. If net EMF did exist, means positive, then the resulting flow of electric current would cause heating in some parts of the circuit, thereby transforming heat from this lower temperature to higher temperature without application of external work. So that is contrary completely. This statement is contrary to this type of flow is contrary to the second law of thermodynamics. So that is not acceptable. So that's why so the net positive, this one that algebraic sum of all the EMF needs to be 0. It should be 0. Okay, then this is okay. Law of intermediate metals.
Yes, sir.
So by the combination of this homogeneous circuit, okay, this combination of this law of intermediate metal and this combination of homogeneous circuit, this makes it possible to insert, okay, or insert a measuring device or a connecting wire C into the thermocouple. So because of these two laws only, it is very much possible to extend the this reference measuring junction with the reference junction by connecting with some other lead wires and also with some galvanometer device to measure the EMF into the thermocouple circuit. At any point we can connect this one. Because of these two laws only, it is at most possible. Without these two laws, we cannot add the lead wires as such. We cannot extend the thermocouple wires. Okay, then third law is called law of intermediate temperatures. So what this law is saying, the thermal EMF developed by any thermocouple of homogeneous metal with its junction at any temperatures T1 and T3 respectively is the algebraic sum of EMF of the thermocouple with its junction at the temperature T1 and T2 respectively, and EMF of the same thermocouple with its junction at temperature T2 and T3 respectively. So this law is nothing but like this. Okay, law of intermediate temperatures. Law of intermediate temperatures. So what this law is saying is, so for example, if you have a two different temperatures, T1 and T2, then the EMF generated because of the difference in the temperature, this temperature is EMF 1, we will say. Okay, then if you have a same junction temperatures T1 and so for example, this is T2 and this other junction temperature is T3. If the EMF generated in between these two is EMF 2 and EMF generated between T2 and T3 is EMF 3. According to law of intermediate temperatures is EMF 1 is equal to sum of the EMF 2 plus EMF 3. That's what the statement of this particular law of intermediate temperatures. Regardless of what is the intermediate temperature, if the EMF, this two temperatures, this T1 is equal to this T1, this T3 is equal to this T2, then the intermediate temperatures, whatever the EMF generated because of the different intermediate temperature, that should be algebraic sum of the EMF. It should be equal to the main EMF. That's the statement of this particular law. Okay, this law deals with the calibration of thermocouple. If the thermal EMFs of several metal versus a reference metal such as platinum, lead are known, the thermal EMF of any combination of these metals may be obtained by algebraic difference. So this law provides that if we know some reference metal wires thermal EMF, then we can predict the other thermal EMFs also, other metals EMF also, how it will be combined and how it will be operated. We can easily know by adopting this law of intermediate temperatures. So when all these three laws are combined, it is evident that the algebraic sum of the thermal EMF generated in a thermocouple circuit containing any number of dissimilar homogeneous conductors is a function of only temperatures of the junction. This allows you can add any intermediate wires in between the thermocouples. So according to the Lord Kelvin, thermocouple can be assumed of the reversible heat engine. So it will be functioning as a reversible heat engine. So is that clear?
Yes, sir.
Okay. So this was the three laws. So tomorrow we are going to see the construction of industrial thermocouple. What are the desirable characteristics? How to construct that one? So what are the other types of thermocouples? What are the lead wires are there? What is the compatible lead wires with the compatible thermocouples? And finally, we will see the thermal wells. Okay, for the protection devices. This one. Finally, we will wind up this unit. Okay, then. Thank you for listening.
Thank you, sir. Have a nice day.
Same to you.